This is lesson 83, VHDL example 54, and in this example we'll write a VHDL program to generate a PWM signal that we can use to control the speed of a DC motor. Let's take a look at this VHDL program. We want to generate this PWM signal where duty is the amount of time the PWM signal is high and period is the period of the PWM signal. We'll make duty and period 4 bits for this example, so each one's a 3 down to 0. And the idea is we'll make a 4-bit counter, and then we'll just count for how long the duty is high and then count for the period. So here's the 4-bit counter. We've seen this before. Signal count 3 down to 0. We have our asynchronous clear, and else on the rising edge of the clock. If count is period minus 1, then we'll reset it to 0. Since we're counting from 0, we'll make it period minus 1, else we just increment the count. So this is our 4-bit counter. And then the output, PWM, will just be 1 if count is less than duty, 1, else PWM is 0. So that's how we'll make the PWM signal. And let's simulate it to see if it works. Here's our clock. I've picked a duty of 4 and a period of D, or 13. So you see PWM goes high when the count is 0, 1, 2, 3, less than the duty. So it's high for 4 clock periods. And then it goes low, and it will stay low until it gets to C, less than period minus 1, and then it will go back high. So 0 to C means the period is actually 13 and the duty is 4. So that's how it works. Now, for a motor we want to generate typically about a 2 kilohertz PWM signal. So how can we do that? Well, 2 kilohertz is 0.5 millisecond period, and if we look at our clock divide table that we had, you see that a Q14 would give us a period here of 0.65 milliseconds, which is more than 0.5. So we need to get at least to Q14 to get up to half a millisecond. Well, we could make a 15-bit counter, but that's more resolution than we need for a motor speed. 8 bits would probably be enough. That would be 255, which would give us 255 different speeds. So if we count back from here, 1, 2, 3, 4, 5, 6, 7, 8, we could use Q6 then as the clock input to an 8-bit counter, and then we would get up to more than 0.5 milliseconds. And in fact, the period that we want, we could just calculate to be 0.5 divided by this 0.65536 times the 255 count, which would mean if we set the period to 195, or C3 hex, we should get a 0.5 millisecond period. So let's write a modified PWM program. We'll make it an n-bit one, generic. Here I set the integer to 16 for default, but if you want an 8-bit one, then in the port map statement where you have your generic map, you just set it to 8. And then here's our duty, would be n-1 down to 0, period is n-1 down to 0. And then this is just similar to what we had before. We need a n-bit counter, so the n-bit counter count is now n-1 down to 0. The asynchronous clear, all zeros, else the rising edge of the clock. If the count is equal to period minus 1, reset the count to all zeros, otherwise just increment the count. And to compute the PWM then, if count is less than duty, PWM is 1, else PWM is 0. So this will generate a PWM signal that we could use to control the speed of a motor. Let's simulate it and see if it works. Here I set the duty to 40 hex and the period to C3. which should give us a half a millisecond, and we measure it here. Here's the period, and you see in fact it's very close to 0.5 milliseconds. We have 499.2 microseconds, you see. So the period is about a period for a 2 kilohertz PWM signal. And by changing duty, then you could change the time that it's high, and this signal then could be used to control the speed of a motor.